Hi and welcome to Unit 1, Topic 3, Video 9 of our video series on proof. And this is the start of proof by induction, which is actually a Unit 3 topic, but it does sneak into the thinking of some of the textbooks and certainly my thinking in terms of covering it off early in proof. So what I tend to like doing is teaching proof by induction and doing it based on summation proofs only, so we won't worry about the other types of proof by induction in this little sub video series, but I do want to go through the idea of proof by induction and show you how you can do it. So on some learning goals and success criteria, you're welcome to have a read of those, and sometimes it's called proof by mathematical induction. So here's some information about it. It's really nice. It takes a little bit to get used to start with, but then it's just a beautiful way of proving something. So theoretically, this is how we do it, in purple there. Show that it works in the first case, and then assume that it works in the kth case. Use your assumption, step number two, to show that it will work in the next case, and conclude it must work in all cases. So let's look at the domino anecdote for this. So let's say you've got this run of dominoes, and here's domino number 1. And let's say also that you know that if domino number k falls, we're saying this one here, then that will definitely knock over domino number k plus 1. You know that's true. So you know it's true for all of them, that if you knock down the previous domino, the next one will fall over. Well, that means that if this domino here falls, then this one will definitely fall. But if this one falls, then this one will definitely fall. And if this one falls, then this one will definitely fall. And if this one falls, then this one will definitely fall. And as you can see, I could go on forever, right all the way up to the back here. What we're saying is that if you can prove a relationship between two consecutive pairs of dominoes, and that is that the previous one will knock the next one over, and then you knock over the first one, they will all fall over. Proof by induction is almost exactly that. So for proof by induction, what we do is we show, first of all, that it works in the first case, and then we show that if it works in the kth case, then and we can prove it works in the k plus 1th case because of the kth case, well, then we can prove that they all work because each previous case proves the next case. And that's going to be the goal of our proof by induction. Now, this is a little bit easier to understand through example. So if you're going to write anything down, these are called the induction steps. And it's a really simple version of it, and it's what you'll do. Now, pretty typically, in an exam situation, there'll be 1 mark here, 1 mark here, 2 to 4 marks here, and then maybe 1 mark there. But this one won't be an implied or an error carrying mark. You'll have to have the rest correct. Or maybe not here, maybe a mark for working as well could come up. And we're going to be working with summation proofs. So what we'll be doing is we'll be showing that it works in the first case, assuming that it works in the kth case, proving that it therefore works in the k plus 1th case, and then concluding. And we're going to start we're going to do 4 examples overall, or 3 examples, but example 1 is 2 separate examples. And I'm going to do in video 1, example 1, A and B, and then in video 2 and 3, we'll do the 2nd and 3rd example, which have some other little things going on. So let's start with example 1A. So in 1A, we want to prove that 2 plus 4 plus 6 plus blah, 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 up to some even number is equal to, or some even number written as 2n, is equal to n times n plus 1. So let's do that using our steps. Step 1. I'm going to prove for n equals 1. So in this case, n equals 1. I've got the left-hand side is just the first term, which is equal to 2. 2 plus nothing. The right-hand side is equal to n times n plus 1, which is equal to 1 times 1 plus 1, which is also equal to 2. So it's equal to the left-hand side, and I've proven it's true. Now, I'm going to do it for step 2. So in step 2, it's assuming that it works for n equals k. Now this is pretty much always going to be a one-line step. So that means we're going to say 2 plus 4 plus 6 plus ... plus 2k is equal to k times k plus 1. all I've done is swap out the n for k. It's important not to double dip on n, so that's why we use k almost all the time. But be flexible with your use of n, k, and other variables. Now, step 3 is the big one. This is the prove that it works for n equals k plus 1. Okay, so n equals k plus 1 is a statement that looks like this. 2 plus 4 plus 6 plus ... plus 2k plus 2k plus 1, which is the next term. So there's one additional term. We've got all of these terms up to k, but then k plus 1 adds an extra term onto that. And we want that to be equal to k plus 1 times k plus 1 plus 1. So it's a grossly unsimplified term there, but we've swapped all the n's for k plus 1's, and I've gone overboard with the brackets, but I really have to in this case. Okay, our problem is here. This is always the problem with the summation. We've got that ... Now I don't know whether this is 2 plus 4 plus 6 plus 8 only, or maybe it's 2 plus 4 plus 6 plus 8 plus 10 plus 12 all the way up to 156. Or maybe it goes to 1,000,000. I don't know what the ... represents. That's the biggest issue I've got. And that's what I'm dealing with. So, how are we going to deal with that ... This will always be taken out. If you've done the right thing, that will be taken out by the assumption step. So have a look at this. That thing is the assumption step, and it also happens to be every term except for the last one in our subsequent n equals k plus 1 step. So what I'm going to do is I'm going to swap that whole thing out for what it's equal to. And my next line with the swap out will be k times k plus 1, and then plus this leftover thing here, 2 times k plus 1. And I could write this over here. This is my right-hand side. But you know what? I'm going to leave that right-hand side alone because this is a proper proof. So I should really pick a side. And I'm going to start with my left-hand side, a little bit like I did up here with my n equals 1. So my left-hand side equals k times k plus 1 plus 2k plus 1. And I cannot stress enough that this thing that I've done here is the biggest step and usually the thing that people understand the least. So make sure that you take some time on this simple example to really think about what we're doing. I've got an assumption step there. I've got something is equal to something else. So I'm taking out the original something and swapping it for the something else. In this case, the k times k plus 1. Okay, but I've got a lot of colours here. So my left-hand side is equal to k times k plus 1 plus 2 times k plus 1. Now, I could expand this. In fact, I'm going to expand this, but I'm going to show you an alternate finish to this in a minute as well. So let's expand it. K squared plus k plus 2k plus 1, which is k squared plus 3k plus 1. Now, that doesn't look like the right-hand side yet, but I can use the right-hand side to guide me. The right-hand side is k plus 1, and then I've got k plus 1 plus 1, which is k plus 2, and this is equal to k squared plus k plus 2k plus 2, which is equal to k squared. Ooh, look at that. I have done that expansion incorrectly. 2 times 1 is 2, so that should be a 2. Hopefully you are sitting there watching this video and just yelling at your screen. That's a 2! Anyway, k squared plus k plus 2k plus 2. So k squared plus 3k plus 2. And this is equal to my left-hand side, which is what I'm trying to prove. So I've done the right thing, and this is perfectly fine. What I've done here works, and we're really happy for you to do that. But there is a little alternate which is just a little bit more elegant. And that is that you could come over here and recognize that k plus 1 is a common factor here. And k plus 1, and you're left with k plus 2. And actually, the right-hand side also equals k plus 1 times k plus 2, and that's equal to the left-hand side, and you're done. So you could do it a little bit quicker if you're a bit clever and you see that link. Also, like I say, don't forget, we know where we're heading. There's a k plus 1 there, and so I'm looking to factorise out a k plus 1 to get my right-hand side, and look at that, it's there. So use the fact you know where you're heading. So that's the end of the proof. All we have to do is prove that for n equals k plus 1, left-hand side equals right-hand side, let me just go back up and show you again before I write a conclusion. So we're asked to prove that 2 plus 4 plus 6 plus blah 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 plus 2n equals n times n plus 1 for all n greater than 1. Now I'm following the induction steps. 1, show it works for n equals 1. 2, assume it works for n equals k and write the assumption down. 3, prove that it works for n equals k plus 1. Add in the extra term, change your right hand side. Use the assumption step to substitute out a series of values that will include the dot dot dot, and then simplify and show that left hand side equals right hand side, and you're done. Now, of course, we do need to do our conclusion. So step 4 will be to write a conclusion that looks something like this. Therefore, as the sum works for n equals 1, it also must work for n equals 1 plus 1, which is 2, and as this needs a capital, it works for n equals 2, it must work for n equals 3, and so on. Now, I would encourage you to read some of the textbook examples of this, read other people's examples. Conclusions will vary a little bit, but you need something like that. And, you know, sometimes it can be worth a mark, and it's the easiest thing to do. So if you've done the rest right, make sure you get a conclusion. Okay, so there is example 1A, and I think I've actually taken a bit of a while on that, so I'm going to do example 1B in the next video. All the best.